All right, our next speaker is Dr. Elvin Rada from University of Elbasan.
Awesome.
I'll apologize. Okay?
Alexander Giovanni in Albania.
Very good. Thank you so much. And title of talk is it is a little bit different from what's posted there. Okay.
Yes,
Multi-Inertial lambda iteration algorithm for endpoint approximation for multi-valued Jaggi-Type F contractions with application to differential inclusions. Yes. So let's start.
It is a little different because this is the last part of my work that I am adding a new type of algorithm that is with multi-inertial lambda iterations. Sorry, can you?
Saying still it is in the approximation of fixed pointers.
Yes. So in this presentation, we will give the background and motivation of our articles. We have preliminaries, our proposal multi-inertial iteration, and approximation theory, William-Hare stability, application to different inclusions. We will have a section with numerical comparison and conclusions and future work. In this case, we develop a mathematically rigorous multi-inertial framework for multivalued Jaggi-Type F contraction Banach spaces. Our proposed method combines multivalued dynamics, endpoint theory, multi-inertial extrapolation, stability results. We will establish the existence of fixed endpoint, uniqueness of endpoints, strong convergence of the proposed iteration, William-Hare stability, and application to different inclusions. Numerical comparison and graphical simulations show
Is something wrong?
Yes, sorry. Yes, now it's okay. I had a problem with the internet connection. So, fixed endpoint theory, as we know, for multivalued operators plays a central role in nonlinear functional analysis, optimization and variation analysis, equilibrium system, differential inclusions, control theory, mathematical economics, nonlinear dynamical system. Classical foundations results include Banach contraction principle, Nadler multivalued contraction theorem, Jaggi rational contraction, and Twardowski F contractions. Now, in recent years, inertial iterative methods have become increasingly important in nonlinear analysis. General inertial philosophy, xn plus 1 equal to t xn plus alpha and xn minus xn minus 1, included inertial term xn minus xn1 that introduced memory effects into the dynamics. The advantages of this are acceleration of convergence, stabilization of trajectories, improved approximation behavior, and numerical robustness. Now, many inertial procedures in literature are formulated in abstract metric spaces. However, inertial expressions such as xn plus alpha and xn minus xn minus 1 require subtraction, scalar multiplication, and vector addition. Therefore, here we have our observation that inertial algorithms are naturally Banach space contraction, not merely metric space contraction. This motivates our present works. Our principal objectives are to construct a mathematically rigorous multi-inertial framework, to develop endpoint approximation theory for multivalued operators, to establish strong convergence result, to derive William-Heuer's stability estimates and to apply the theory to multi-valued different inclusions. In the end, we have even a section of numerical comparison. Our works combines multi-value analysis, inertial dynamics, stability theory, and differential inclusions. Now, in this case, let us denote with CBA the family of all empty closed bounded sets of a Banach space E. In this case, for AB in CBE, define dxa, in this case, the infimum of the norm x minus a from A, comma A. Here, of course, we have the definition of well-known Hausdorff matrix. But in this case, AJB is the maximum of supremum DAB, supremum DBA. This matrix will allow us to compare multivalued images. In this case, we have T from E to CBE, definition of a fixed point. X is from E is a fixed point if X is part of Tx. In this case, we will have even definition of endpoints. When endpoints Tx will be family of X. Endpoints are stronger objects than fixed point in this case, and they allow us stronger convergence and stability results. Now, here we have T a multivalued operator, Te into CBE is called a multivalued Jaggi-Type at contractions if it will satisfy this inequality. Down plus FH Tx Ty smaller or equal than F A x minus y plus BD x Tx plus CD y Ty, where A, B, C are greater than 0 and they have the condition A plus B plus C smaller than 1. And this class, as we know, simultaneously generalize Banach contraction, rational contraction, non-Donaldovsky and contractions. In this case, is our new proposed multi-inertial algorithm. In this case, from 2 point x0, x1 from E, it defines y n equal to xn plus alpha n, xn minus 1 plus epsilon n. Zn will be xn plus beta n, xn minus 1 plus rho n, and un will be xn plus gamma n, xn minus 1 plus omega n. If we choose Vun from T of Un, we'll define xn plus 1 in this form, 1 minus lambda n, yn plus lambda n above 2, zn plus lambda n above 2, Vn plus theta n. In this case, we'll assume that the errors or the noises, their sum of the norms will be finite. In this case, our algorithm contains 4 important components. We have triple inertial extrapolation, alpha and beta and gamma n. We'll have multivalued operator dynamics, Vn from T-Un. We'll have relaxation mechanism, this is lambda n, and the perturbation and error controls are epsilon n, rho n, omega n, and theta n. So this creates a significantly richer natural structure than the classical one-step methods. Because classical natural methods use only one extrapolation types. Our framework introduced 3 different inertial levels, Yn, Zn, and Un. In this case, if we give some interpretation, Yn will be primary inertial trajectory, Zn will be secondary extrapolation, and Un operator evaluation time. The advantages of this type of methods are richer approximation dynamics, more flexibility, better perturbation control, and stronger ability properties. Now, we assume the existence of the endpoint x star from the NT. NT is this set. In this case, satisfying the contractive conditions, h dx dx star smaller or equal than q norm x minus x star, where q is from 0 to 1. In this case, the multivalued images become progressively closer to the endpoint. The constant q measures the contraction density. The Hausdorff metric controls the distance between multivalued sets. The endpoint acts as a globally traction states. Since the x square in this case is x square set, the endpoint behaves as invariance Newton under the multivalued. Now we have to prove the uniqueness of the endpoint. Under the endpoint contractive conditions, we will have that endpoint x star is unique. Let us assume we have two endpoints, x star and y star. In this case, we will have tx star equal to x star and ty star equal to y star. If we'll apply the Hausdorff contraction, h dx star ty star, in this case it will be smaller or equal than q norm x star minus y star. Since x star minus y star is h tx star ty star, we obtain that the norm of x star minus y star is smaller or equal than q x star minus y star. And in this case, because q is smaller than 1, we will have that x star is equal to y star. The second is the main strong convergence theorem. Let us assume we have two kappa 1 and kappa 2 such that kappa 1 plus kappa 2 smaller than 1, where kappa 1 is 1 minus lambda above 1 minus q, 1 plus alpha bar, and kappa 2 is 1 minus lambda above 2, 1 minus q, alpha bar. In this case, our proposed multi-iteration lambda converges strongly to the endpoint xn to x star. This means that the iterative trajectories converge in norms, inertial perturbations remain controlled, and point is globally attractive, and the convergence is preserved despite multivalued dynamics. Now, here we have the key recursive inequality. The convergence analysis reduced to the recursive estimate. Sn minus 1 will be smaller than 1. K1 Sn plus K2 Sn minus 1 plus Rn, where Sn is the norm of xn minus x star, and the perturbation term is Rn 1 minus lambda n, the norm of epsilon n plus lambda n above 2 rho n plus lambda n q above 2 omega n plus norm of theta. In this case, Sn measures the approximation errors, K1, K2 describe inertial influence, Rn controls accumulated perturbations, and summability of Rn guarantees asymptotic stabilization. Applying this sequence gamma yields Sn minus 0. In the original paper, R solve the level. Here we are giving the main results. The convergence conditions in this case become 1 minus lambda above 1 minus q, 1 plus 2 alpha bar smaller than 1. Hence, the inertial coefficient must satisfy alpha bar smaller than 1 above 2, 1 above 1 minus lambda to 1 minus q minus 1. In this case, this means that we have some conditions because inertial acceleration cannot be arbitrarily large. Excessive memory effects destroy convergence, and the theorem provides an explicit quantitative admissibility bound. And Our convergence depends only on Q, lambda n, and alpha. After that, we'll discuss about linear stability. In this case, we consider approximate trajectories satisfying x tilde n plus 1 minus an, norm smaller or equal than epsilon. When an denotes the exact iteration operator. Here the question is, do the approximate iterative trajectories remain close to the exact endpoint? And the answer is in the following theorem. Our proposed multi-iteration that we gave before is stable, is William higher stables, and moreover, the limit of the supreme when n tends to infinite of the norm of x n tilde minus x star is smaller or equal than epsilon above 1 minus k1 and k2, where k1 and k2 are the constant that we defined above. In this case, we can say that approximate trajectories remain close to the exact endpoint. Numerical perturbations do not propagate uncontrollably. The iteration is robust under computational errors, and the stability constant is easily computable. This is particularly important for numerical implementation and application to different inclusions. We will see later both of these cases. Now, here we have our example. Let us consider second-order differential inclusions. X second t, it is in minus phi t xt, with t from 0, with the conditions x0, x1 equal to 0. This problem appears in control system, non-smooth dynamics, set-valued mechanism, differential games, and nonlinear evolution systems. In these games, using Green's functions, GTS, t1 minus s for t smaller or equal than s, and s1 minus t for s smaller or equal than t. In this case, we'll define the multivalued Hammerstein type operator tx that would be y from e, such that yt is the integral from 0 to 1 GTS US ds. US is from the set phi xs. In this case, this problem is transformed into an endpoint approximation problem from T. In this case, let us assume that h f tx phi ty is smaller than lx minus y. In this case, we're assuming that L is from 0 to 8. Then h dx dy will be smaller or equal than L above a x minus. So if we have Q L above 8, in this case, Q will be 0 to 1. So we'll have the abstract endpoint theory applicable. Now, here's the application of our multi-inertial algorithm with 3 steps. As we said before, yn will be xn plus alpha n x n minus xn minus 1 plus epsilon n. Zn will be xn plus beta n xn minus xn minus 1 plus rho n. Un will be xn plus gamma n xn minus xn minus y plus omega n. In this case, we'll choose measurable selections, phi n s from the big phi s uns. We'll define VMT, the integration from 0 to 1 to the green GTS phi ns. And we'll generate this iteration, this algorithm. Xn plus 1 will be 1 minus lambda n, yn plus lambda n above 2, zn plus lambda n above 2, vn plus zeta. The theorem is under the endpoint assumption of the associated multivalued integrals operator, the proposed multi-inertial iterations converge strongly to a cathode solution of the different inclusions. The main consequences of this theorem are that the abstract endpoint theory becomes applicable to nonlinear boundary value problems. The iteration generates an explicit approximation procedure, converger occurs in C01R, and measurable selector techniques connect multivalued dynamics with integral operator theory. So this framework provides both endpoint-based solvability and constructive approximation. Now, after that, we have a comparison model to show why our type of iteration is better in some directions than the other well-known type of iterations. If we consider the multivalued mapping Tx, it would be 0.8x minus 0.2x with
Dr.
x
Rada,
from...
you have 2 minutes.
Okay. So in this case, x star is 0 and t0 is 0. Moreover, h tx t0 will be 0.8x. So hence the endpoint contrary condition holds for q equal to 0.8. This is a genuine multivalued example because every tx contains 2 possible images in this case. After that, we have compared iterative schemes. We have bigger iteration, xn minus 1. We have made these conditions 0.8xn, xn plus 1, 0.84xn, depending with a variable of n. Single inertial iteration, xn plus 1, 0.84, xn plus 0.15, xn minus 6 minus 1. And our multi-inertial iteration, xn plus 1 equal to 1 minus lambda yn plus lambda above 2 zn plus lambda above 2 vn. In this case, a constant r 0.8 for lambda, alpha 0.15 for beta 0.1 and for gamma 0.05. In this case, the key advantage appears in the multivariate selection step. T1 will be 0.un minus the second value is minus 0.2 un. The classical conservative choice use Vn with 0.8 un. The proposed multi-inertial scheme can be used by the stabilizing selection Vn minus 0.2 un. In this case, our method is better because it combines 3 inertial predictors. We have a stabilized multivalued selection and the relaxation for lambda. Here is a table about the numerical errors. If we will have the error en xn minus x star, we have with a number of iterations for the example it would take before. And here we have the graphic, the plot for the convergence comparisons. So in this case, we see that our methods is better because the error is smaller than all other types of iterations. This example shows that the proposed method can be advantageous when the operator is generally multivalued. The method is better here because it does not only follow one conservative branch of the multivalued map. Instead, it combines several extrapolated states and using a stabilizing selection from the multivalued image. So the proposed multi-inertial iteration can exploit the intentional structure of multivalued mappings more effectively than classical one-step iterations. They support the relevance and of the method for multivalued nonlinear problems and different equations. So the conclusions of our paper are the development of a mathematically rigorous multi-inertial framework for multivalued rates and point approximation theory in Banach spaces, strong convergence and Williams stability results, application to nonlinear differential inclusions, numerical and graphical validation of the theoretical analysis. The numerical experiments show that the proposed method can exploit stabilizing multi-value selections more effectively than several classical one-step procedures. So our proposed framework combines multi-value analysis, inertial dynamics, stability theory, and differential equations. Future research directions include fractional impulsive differential inclusions. Both the fractional differential are a field that is studying a lot of applications in the last years. Another stochastic multi-inertial dynamics, adaptive inertial parameter strategies, variation inequalities in equilibrium systems, generalized Banach and modular spaces, machine learning inspired inertial systems, large-scale numerical implementations. Other important directions is the development of optimized multi-value selection strategy for accelerated endpoint approximation. Here are the main references. One of these are all well known. One is one article of a work that I made for one valued or single valued function. And in this article, I tried to adapt it for multivalued function. Thank you.